Yes, Carlo.
Sir, question lang. On the previous problem sets,
Uh-huh.
he knows, is the answer key posted somewhere
Ah, yeah.
on the previous ones?
Actually, hindi ako naggawa ng answer key.
Oh, sorry.
Uh,
Just
yeah, I just saw to it na magko-comment ako ng todo dun sa mga submissions nyo para hindi na ako mag-upload ng answer key. Saka para madali ko ring ma-recycle if ever yung questions ko next semester. So hindi ako magli-leak ng answer key. Pero if you have some
oh,
questions about the previous and the previous problem sets, you can consult with me na lang kaysa mag-upload ako ng answer key, right? Ina-avoid ko yung pag-leak nung information.
okay. I was just wondering kasi not all questions, di ba nagpipick lang ng 2 out of 3 or something like that. So
Ay,
not
oo
all
nga, no?
questions were.
Mhm. Oh,
So
nice
just
point.
wondering.
Yeah. Actually, yung ginagawa ko ay chine-check ko siya on the fly. So, kung sino yung magsusubmit, titingnan ko yung work nila, tapos ko-commentan ko. Kaya hindi ako nagagawa ng answer key beforehand. Pero let's see. Let me think about that. Siguro, for the previous problem sets, I don't think you will need them except if you will prepare for the finals. So probably I'll spend a good or some days in my Christmas break to kind of prepare answer keys. Pero pag-isipan ko, all right? So kasi yun nga, ayokong mag-leak yung answers to the questions. Pero just let me know, chat nyo lang ako kung talagang kailangan nyo, then I'll work on it later. Okay?
Okay,
Over the
thank you.
break. Okay, you're welcome. So yeah, the deadline for the problem set is tonight, right before midnight, if I'm not mistaken. So hopefully, guys, nakapag-upload na kayo. Admittedly, medyo tinas ko ng konti yung konti ba? Hindi ko alam kung mag-agree kayo or hindi. Yung level ng problem set just to see how you're doing. I guess the last two problems, either of them is quite new to say the least kasi meron ako doon mga terms na dinefine na hindi ko diniscuss. Pero this is a nice training for you because when you're doing your thesis or you're doing your research work once you graduate, from time to time you will encounter things that were not defined in your formal classes, or you are forced to describe or to define certain concepts na wala pang gumagamit before. So it would be a nice exercise for you to get acquainted to this type of problems. So meron do mga terms like limits at infinity kahit na-define siya sa Math 36 pero hindi natin siya define sa Math 155. But the training that you have gotten hopefully from this course will allow you to work with these concepts even without the teacher explicitly discussing them in class. Pero pag nakita niyo yung definition, kaya niyo siyang i-connect dun sa mga previous concepts na na-discuss natin, and you can write a formal proof. And honestly, I just want to see how you perform with those type of problems. Mas mabigat yung second question doon kasi it's about absolute continuity. So I'm not sure if somebody tried answering that problem. Ang na-checkan ko pa lang siguro mga apat na piraso or apat na problems. But I'll try to grade it over my vacation. Oh, by the way, guys, I don't know if I have announced that I will be on vacation leave starting tomorrow until Wednesday morning. So that means I won't be able to meet you on Tuesday, and I am thinking whether to record the lecture for Tuesday, or I'll give you a free day off. Siguro para makapag-relax kayo ng konti kasi nahirapan kayo sa problem set on Tuesday. And I'm looking at the calendar. We will be talking about Unit 5 for the rest of the semester. And there are 5 sections to it. And I think we still have 5 meetings, including December 21, or 6 meetings, including December 21. So I think I can still manage even if I declare December 7 as a class holiday. So ganun na lang siguro yung gawin ko. We won't meet on Tuesday. This coming Tuesday, that's December 7, all right? But I'll give you a homework, one problem homework para sa Unit 4, para sa derivatives. So I'll just pick one problem from the exercises in the lecture notes, and I will ask you to submit it probably on Friday next week. So maiksi lang para lang masabing meron tayong homework sa unit number 4. And then we will have the last problem set probably bibigay ko siyang last day ng classes ay December 21, no? So probably the last problem set will be given December 15. Okay na ba yun? December 15, then the deadline is December 21. But I can accept submissions until the 24th. So bago kayo mag-Noche Buena, sige, papayagan ko pa kayo mag-submit. But if you would not like to bring home some exercises for the Christmas break, then pwede kayo mag-submit by December 21. I'll see to it that the last problem set is doable on the period December 15 to December 21. So pero couple more days kung gusto niyo mag-relax lang yung paggagawa ng problem set. So papayagan ko kayo hanggang December 24. All right? Is that okay with you guys? Or meron pa ba kayong mga requests? I'll try to grade the problem set over the weekend. So pagka na-bore na ako dun sa pupuntahan ko, magbubukas sila ako ng Canvas at mag-check nung mga works nyo. So you can still send me emails and chats via MS Teams if you have some questions. I'll try to respond as soon as possible, but since vacation mode, baka hindi ako makasagot kagad as prompt as before. Okay? So now we're off to the last unit of Math 155. Hold on guys, double check ko nga. So ngayon ay 5.1, sa December 9 ay 5.2, 5.3 sa 14, 5.4 sa 16. So I think we're still good. So holiday na lang tayo ng December 7. Pagka kukulangin ako ng oras, magre-record na lang ako ng video ng ganitong lecture, tapos pwede nyo siyang panoorin kung kukulangin ako. Pero I think I can still manage with 4 meetings for the entire unit. Okay? All right, so we will start talking about Riemann integration in R. Kasi nga, sabi natin sa Math 155, nire-retrace lang natin yung mga natutunan nyo from elementary calculus, from concept of limits up to the concept of integrals. So ngayon, i-generalize natin yung konsepto ng integration na natutunan nyo mula sa Math 36. And probably I can make some commentary about the integration that we know. Actually, it is called Riemann integration because when you go to graduate studies, you will learn na may mga shortcomings yung Riemann integration na prompted mathematicians to actually develop a more generic definition for integrals kasi medyo limited yung mga functions na integrable. May mga functions na super simple siya na kung iisipin mo, dapat meron tong integral. Pero hindi siya kayang bigyan ng integral in the sense of Riemann. So meron tayong tinatawag na Lebesgue integral or some other advanced integrals for further analysis courses. Pero yung Lebesgue integral sila na yung parang natural extension ng Riemann integration. Okay? But for Math 155, we will stick to Riemann integration. Siguro pwede ko palang ipagawa sa final project yung Lebesgue integration no, na reading assignment. But let me think about the final project over my vacation. So, yeah, pag-isipan ko siya para masabihan ko na rin kayo kagad kung ano yung final project. Okay? So today we'll tackle section 5.1, which is about defining Riemann integral and look at its basic properties. And then next meeting, we'll talk about the integrability criterion. Alin lang mga functions ang Riemann integrable. Okay? Tapos papakita natin na merong mga functions na napakasimple na hindi Riemann integrable, which prompted some mathematicians to develop a more general version of integration in the set of real numbers, which is extendable also to the realm of complex numbers. And then after that, we will look at the properties of the Riemann integral. Most of these ay nakita nyo na sa elementary calculus, like the additivity, what else? The linearity of the integral operator, and so on. And then hopefully, ito talaga yung dapat kong matapos, the fundamental theorem of calculus. Kasi nga, kaya ang pangalan niya ay fundamental theorem of calculus kasi siya yung isa sa mga pinaka-importanting theorem sa calculus. So it would be a shame to finish advanced calculus without even tackling the fundamental theorem of calculus. All right. So that's our schedule for the rest of the semester, or this is our menu for the rest of the semester. And let's start with section 5.1. So ito ay formalization lamang nung inaral nyo sa elementary calculus. Na sa elementary calculus, may dalawang paraan kasi ng pag-develop ng integral. And sa elementary calculus, pareha siyang dinidiscuss. Number one is the concept of the integral as the inverse process of the derivative, right? So yung differentiation at saka integration, sila ay inverse processes ng isa't isa. So kaya nga, halimbawa, natutunan nyo na sa previous chapter sa inyong elementary calculus na halimbawa kung ang f of x natin ay say sin x, right? Then alam natin yung derivative ni f ay cosine x, right? Then ang gagawin, sasabihin ng teacher nyo, okay, so yung integral ay inverse process lang ng differentiation. So pag pinakuha ko yung integral of cosine x dx, you will be looking for the function who, when differentiated, will give you cosine x dx. So hanapin nyo ano yung mga functions na pag differentiate ko, ang sagot ay yung integrand na cosine x. And by knowledge of derivative theorems from the previous sections in your elementary calculus, you can say, okay, this is sine x, but I know that the derivative of a constant is equal to 0, so I can add any arbitrary constant to it. So this gives a false impression that integrals is tightly hinged on the concept of derivatives, okay? Tapos nabanggit ko nga yung derivatives or yung pagiging differentiable, napakalaki ng requirement niya. So it would be a shame to tie the concept of integrals to a very restrictive class of differentiable functions. Kasi kung ganun yung sasabihin natin, dapat siya ay derivative ng isang function. So ang sagot mo lagi dito ay mga differentiable functions, okay? Which is true if we will look at the fundamental theory of calculus. Pero yun nga, parang napaka-dependent nung development ng integrals in this way, thinking of it as the inverse process of the derivative. That's why in one of the names for the integral is the antiderivative, right? What is the function that when differentiated will give us cosine x? But why not develop the concept of integral as a field of its own, or a field of study in its own right? Okay? Kaya i-discuss dun sa siguro later chapter ng elementary calculus yung idea ng pag-approximate ng area ng isang plane region. Tapos makikita natin na ang definite integral lang pala ay yung area under the curve. So, halimbawa, meron ako diyang xy axis, right? X, Y, okay. Then I have A and B here, right? And then I'll consider a continuous function on the closed interval AB, right? So say this is my function f of x, okay? And then we will say that the area bounded above by the curve y equals f of x and the x-axis is just equal to what we call the definite integral of the function f over the interval AB. So this region here, okay, kulayan ko lang siya. Yung area daw ng region na yan is what we call the definite integral from a to b of f of x dx. Now, with the aid of the fundamental theorem of calculus, which we will discuss later, we will have a neat way of calculating the value of the definite integral. Makikita natin later na ito lamang ay capital F of b minus f of a, where capital F is an antiderivative of the function little f. All right? Pero paano siya talaga binuo? Naalala niyo ba? Paano niyo kinompute yung area nito without FTC, without the fundamental theorem? So I hope you remember you did divide the interval AB into several subintervals and then approximated the area of each rectangular strip induced by the subdivisions in terms of the areas of those rectangles, right? So ang ginawa nyo, okay, x1, naglagay ako dito ng x1, x2, x3, x4. Alright, kunwari yan yung mga subdivision points ko. Tapos hahatiin ko siya dyan. Okay. Gusto kong i-approximate yung area kasi yun yung idea ko ng value ng definite integral. Paano ko siya i-approximate? Gagamitin ko yung area ng mga shapes na alam kong computein. For instance, rectangles. So halimbawa, pipiliin ko yung value sa left endpoint of each of the subintervals to be my height. So ibig sabihin, yung unang rectangle, ito yung ito yung itsura. And then I will compute the area of the rectangle, and that's fine. I will just compute how wide the rectangle is. Let's call it the change in x, the first change in x. All right, so parang delta x sub 1 siya. That's the distance, that's the width of the first subinterval. Tapos yung height, gagawin ko siyang f of x sub 0, which is the function value here at the left endpoint, right? And then I'll say that the area of the region is f of x sub 0 times delta x sub 1. So ayun yung magiging approximate ko para dun sa area nung region bounded by y equals f of x and the x-axis on the interval a comma x sub 1. So essentially, I will be getting this area here. Kaya lang makikita nyo, meron tong error involved. Ito ay overestimate. Itong orange region dito, yan ay overestimate para dun sa area ng region. Okay? Now, I will do this for all of the subintervals. So again, on the second interval, magdodrawing uli ako ng rectangle. Ang gagamitin ko uli, halimbawa, ay yung nasa left endpoint pa rin. Okay? Ito yung makukuha kong rectangle. Okay? Tapos, yung area will still be change in x, but this is the second change of x. So that's the width of the second rectangle. And then the height of the second rectangle will be this guy, f of x sub 1. And then the estimate for the area will be the green portion. And here we see there is an overestimate again, amounting to the orange region. Okay? And then you will do this, and then you will add up the areas of these rectangles to get the approximate for the area of the yellow region. But of course, you will see, or you can imagine, that indeed there are errors involved in this approximation. Okay? So ano yung ginawa nyo para mabawasan yung error or completely ma-eliminate yung over at saka underestimate dito sa area, dito sa approximation process na to? So nga, review lang to ng elementary calculus. Ano nga yung ginawa natin nun? Paano natin natanggal yung error? What was the strategy employed then? Kalimutan nyo na? Or gagawa pa rin kayo ng problem set? Oh yes, Carlo?
Sir, try lang.
Sige.
Is it using the midpoint or the right end?
Okay, yeah, that could work. Pwedeng gawin ay pumili tayo ng mas magandang basis para dun sa maging height ng mga rectangles. Kasi wala namang nagsabi na ang gamitan natin ay left endpoint. It's kind of an arbitrary choice on my part. So what Carlo is saying, perhaps we can use the midpoint to give us the estimate. So halimbawa, dito sa x4 to b, okay, yung midpoint daw yung gamitin ko. So ito yung magbibigay sa akin ng height. Right? Tapos, ito yung magiging estimate ko. Alright? So, ito yung magiging estimate ko. And we are hoping that the overestimate here will be compensated by the overestimate here. Over ba yan o under? Ito yung overestimate, tapos ito yung underestimate, and we hope that they will sort of compensate for each other. So that's one possible improvement, or one possible way to improve our calculations or our approximations here. Kaya lang medyo depende rin yun dun sa itsura ng function. Baka naman yung function ay napaka-crazy ng pag-behave on a certain subinterval, then choosing the midpoint might not help us at all. All right? Or pwede kang gumamit ng right endpoint. Pero the idea is arbitrary pa rin yung choice kung ano yung x sub I na gagamitin ko. Actually, you could use any x sub I on each of the subintervals. You can pick any representative from there. But that's a good try though. That will work for some functions, okay? But if I want to get the exact area, what can I do? I think Rexter has something to share. Yes, Rexter?
Ano po sir, paliliitin po ng paliliitin yung mga width by yung paparamihin po ng paparamihin yung mga interval.
Okay. Yeah, probably that will work. What Rexter is suggesting is why not make our rectangles thinner and thinner and thinner? Okay? Kasi kapag ka pinaliit natin, halimbawa ito, okay? Pinaliit ko ngayon, so ito na yung bago kong subinterval halimbawa. Okay? So this would be, magdagdag ako dito ng x5. So from x3 to x5 instead of computing x3 to x4 right away. Now, kung pipiliin ko ay halimbawa midpoint, yung gagamitin kong height, okay? So this will be the area of this very thin strip or very thin rectangle, and you will see na almost negligible na yung error in the approximation. And imagine this being done all throughout the interval, meaning we will be using thinner and thinner and thinner rectangles in order to approximate the area. So mas maninipis yung mga rectangles. So parami sila ng parami, pero mukhang yung area or yung summation ng mga areas nila ay magiging mas malapit dun sa area ng actual region. Okay? Tapos yun nga yung ginawa nyo, pinapayat ng pinapayat yung mga rectangles. So that means pag mapapayat na mapapayat yung mga rectangles, we can say that the widths are approaching 0. So you can take the sum of the areas of the rectangles, but also letting the width of each rectangle to approach 0. So gumamit tayo ng konsepto ng limits, right? We took the summation of the areas of the rectangles and took the limit as delta x approaches 0. Gusto natin thinner and thinner yung mga rectangles na ginagamit na halos wala na siyang width. Alright? Gusto natin mag-approach ng 0 yung width. Or another way of looking at it is considering infinitely many subintervals. Okay? Kasi nga, kung maninipis na maninipis yung mga rectangles, so ibig sabihin, kailangan natin ng napakaraming rectangles para mapunuan yung buong interval AB. So ibig sabihin, instead of taking delta x to approach 0, an equivalent approach is to let the number of subintervals to approach positive infinity or to be indefinitely large. And we guarantee Okay, I hope I'm back. Sorry, guys. Internet problems. Can you hear me now? Hello, guys.
Yes po, sir.
Okay, thank you. Sorry about that. Uh, um, so yeah, walang nakakaligtas sa internet connection problems. Pero let me join again using my. Okay. All right. So where was I cut off? Doon sa discussion ng. Okay. So I think we were still able to discuss yung konsepto ng pagtitake ng limit as the number of subdivisions increase without bound. Hold on. I think I was cut off again. So yeah, let me try screen sharing again. Come on. Okay, there we go. So we were talking about taking the limit of the sum of the areas of the rectangles as the number of subdivision points increases without bounds. At ganun din pala yung process, paparamihin lang natin ng paparamihin yung mga data point, yung mga subdivision points na ginamit. So essentially, magiging super, super small yung mga subintervals. So that means the choice of the height for each of the rectangles would be immaterial. So kaya pwedeng pumili ka nga lang dyan ng kahit anong arbitrary point sa buong subinterval para siya yung mag-serve or magbigay sa atin ng height. I could have chosen this one. Kasi essentially pala later in life, kukunin ko rin yung limit as the number of subdivision points increases. Tapos pag super thin na yung mga rectangles, parang paunti na ng paunti yung choice mo para sa mga exabytes. At pag sobrang liit niya na talaga, yung function value sa mga numbers within the subintervals would be very close to each other. So they will have no significant difference from each other. So that's why in the long run, and when I say long run, ibig sabihin, pag sufficiently large na yung number of subintervals you used, nagiging immaterial na yung choice ng mga exabytes na ginagamit. So ito yung development ng definite integral without going through the concept of the derivative, all right? And we'll try to explore this more or to try to formalize this discussion in section 5.1, okay? So tingnan natin paano siya i-develop in a more formal way. But still, it would be just taking a look at the areas of those rectangles, okay? So we begin our discussion by defining what is a partition inducer of a closed interval. So we'll consider a closed interval, do natin i-evaluate yung integral ng isang function f. We don't have the conditions yet for the function f, basta i-assume natin na the function f is nice enough that will give us a value for the integral. Okay? Pero dito wala pa pala siya. Titingnan pa natin later kung kailan natin masasabi na may integral yung isang function. Okay? So but our main point here is rather than looking at the function itself, tingnan muna natin yung interval. Okay? So let's consider a closed interval AB. Ang isang set of elements of the interval is called a partition inducer if it is an ordered list such that increasing yung pagkakasulat ng mga elements ng set. So si set P should be treated as an ordered set. Okay? Hindi siya yung usual set na hindi nagmamatter yung ordering. Pwede nyo siyang tingnan as a truncated sequence. Okay? So magiging partition inducer siya kapag ka si x0 is strictly less than x1, strictly less than x2, and so on. All right? But x sub 0 must be equal to A, and x sub n must be equal to B. So yun yung condition para maging partition inducer. Pinangalanan siyang ganon kasi ang idea dapat yung mga x sub i's na nandoon kay P, sila yung magsasabi kung ano yung pagkaka-partition nung interval AB into several subintervals. So ito si A, ito si B, ito yung tatawagin kong x sub 0, ito yung gagawin kong x sub n. Alright? Tapos ito si x1, dapat strictly strictly greater than A siya. Si x2 dapat strictly greater than x1, x3, x4, and so on. Kaya siya partition inducer kasi sila yung boundaries dun sa partitioning ng closed interval AB. So here, from x sub 0 to x1 is an interval that is disjoint from the other subintervals induced by the elements of the inducer. Okay? So, ganun din ito. Si x1 to x2 ay disjoint mula sa iba pang mga intervals na mako-construct using the function, the ordered set P, all right? And so on. And when we take the union of all of these subintervals form, yung x2 to x3, x3 to x4, x4 to x5, and so on until x sub n to x sub n minus 1, we will get back the ordered pair. We will get back the closed interval AB. Kaya crucial na dapat increasing yung mga exabytes. Kasi magagaranti niya na non-overlapping yung mga subintervals na mapoform using the elements of capital P. And also, it is important that x sub 0 is equal to A and x sub n is equal to B. This will guarantee that the union of the subintervals formed by the elements of the partition inducer will give us the closed interval AB, right? Kasi kapag si x sub 0 ay hindi A, ibig sabihin merong maliit na portion from A to x sub 0 na hindi kasama dun sa partitioning. Okay? So kaya kailangan yun yung conditions para maging partition inducer. So basically what the partition inducer does, it creates a partitioning of the closed interval. Okay? Now we will define some more things. The delta exabytes, as we have seen in our prelude kanina, can be defined to be x sub I minus x sub I minus 1. And since we said that P is an ordered set, actually it's an increase strictly greater than x sub I minus 1. And we can denote it by either delta x sub I or absolute value of interval II, right? Yung interval II, siya lang yung interval from x sub I minus 1 hanggang x sub I. And this guy denotes the length of that interval. Okay, yung absolute value ng isang interval, siya yung length ng interval. Okay? Now, to illustrate this quickly, let's consider the closed interval 0, 2, all right? So si P1 ay isang partition inducer ng closed interval 0, 2 kasi increasing yung mga element ay yung pagkakasulat ng set P1, all right? 0, 1, and then 2. The first element is the left endpoint of the interval. The last element of the inducer is the right endpoint of the interval. And again, it makes sense that this is a partition inducer because the numbers 0, 1, and 2 will induce a partitioning of the interval 0 to 2. So 0, ito si x sub 0, ito si x sub 2, tapos ang x sub 1 natin ay si 1. Ibig sabihin, these three elements of P1 induces a partitioning of the closed interval 0 to 2 into two intervals. First one is interval 0 to 1, which is of length 1. And second is the interval 1 to 2, also of length 1. Okay? And then when I take the union of the closed interval 0, 1 and the closed interval 1, 2, makukuha ko pabalik yung closed interval 0 to 2. And these two intervals are disjoint except for the boundary point. Okay? Wala na silang ibang common elements other than the boundary points. Okay? Now, the second set, P2, is not a partition inducer. And actually, partition inducer din pala siya kasi 0, 1 half, 1, and 2. This time, this will partition the set, the closed interval 0, 2 into three intervals. The first one is the interval from 0 to 1 half. That would be of length 1 half. Next is the interval 1 half to 2, which would be of length 1 half. And then the third one is the interval 1 to 2, which is of length 1. Okay, and when I take the union of those subintervals, I'll get the closed interval 0 to 2, and these intervals are pairwise disjoint except possibly for the boundary points. Okay? Pero si P3, hindi siya partition inducer by looking at the definition of the partition inducer kasi hindi siya increasing. One precedes one half. So hindi niya na-satisfy yung pagiging strictly increasing ng ordered set. And it doesn't make sense to use P3 as a partition inducer kasi yung unang interval, let's see, yung unang interval ay 0 to 1. Okay, that's fine. This is our first interval. That's I1. Okay. Yung second interval would be 1 to 1 half. So 1 to 1 half, it doesn't make sense to have an interval from 1 to 1 half. Even sabihin mo, okay, baliktarin ko lang. So 1 to 1 half. So halimbawa, ito yon, 1 to 1 half or 1 half to 1. All right. If we will accept yung baligtad na left at saka right endpoints, hindi pa rin ito nagme-make sense as a partitioning. Kasi overlapping yung I1 and I2. All right? So kaya si P3 hindi siya nagme-make sense to be a partition inducer of the closed interval 0 to 2. And the same thing goes for P4. Hindi rin siya partition inducer kasi kahit strictly increasing yung mga elements ni P4, hindi naman siya nag-start dun sa left endpoint ng given closed interval. It started with 1 instead of 0. So it means that kung titingnan mo yung partition induced or yung division induced by P4, ito yung 0 to 2. Nag-start siya kay 1 hanggang 1.5. Ito yung kanyang I1. And then 1.5 to 2, yan yung kanyang I2. However, we didn't cover the entire closed interval 0 to 2. We are missing a huge part of that closed interval. So hindi siya isang partition inducer ng closed interval 0 to 2 kasi hindi siya nag-start kay 0. Okay? But you can say that P4 is a partition inducer for the closed interval 1 to 2. Okay? But not from 0 to 2. Okay? Now, saan natin gagamitan yung partition inducer? Gagamitin natin yung konsepto ng partition inducer para ma-define yung lower at saka upper sum. Usually these are called the lower and upper Riemann sums. Perhaps let's include that in our notes here. So the lower and upper Riemann sums. So the upper Riemann sum of a function f with respect to a partitioning P, all right, is given by this. So ang notation natin para sa upper Riemann sum ay capital U. It will take two variables kasi yung pagko-compute ng upper Riemann sum ay nakadepende sa dalawang bagay. Ano yung function na kino-consider mo? At ano yung partitioning ng function anong subinterval kung saan naka-define yung function. All right? So kaya dapat may dalawang inputs yung upper Riemann sum. Okay? And how do we compute the upper Riemann sum? We will take the summation of products of the form capital Mi times delta x sub I, right? So in the case of our drawing kanina, dun sa pag-compute natin ng rectangles, pwede nyo itong tingnan as the area of a rectangle. So here the rectangles will have width delta x sub I, okay? Pero yung height ay ano? Yung height component daw ay capital M sub I. But what is capital M sub I? Capital M sub I is the supremum of all function values over the interval or the subinterval I sub I. So ibig sabihin, kaya siya tinawag na upper sum or upper Riemann sum. Kasi ang kinukuha ko ay yung pinakamatangkad na or yung binubuo ko yung pinakamatangkad na rectangle on a certain subinterval. Okay? So kasi nga sabi natin sort of arbitrary yung pagpili ko ng height para dun sa mga rectangles. So here, going back here, hindi ko pipiliin yung left endpoint o yung right endpoint o yung midpoint ng mga subintervals. Halimbawa sa pangatlong subinterval, I will use this as my height, not because it is the left endpoint, but because this value of f is the supremum. Let's call this f of x star. This is the supremum of all function values over the interval AB. Siya yung pinakamalaking function value doon sa, hindi pala interval AB, doon sa subinterval x2 to x3. And that's what what we are going to do. Sa bawat subinterval, ang pipiliin mong height ay yung maximum o yung supremum ng mga function values sa closed interval na yon. And hence the name upper sum. Kasi ito yung mga pinakamalalaking rectangle. All right? Analogously, we can define the lower sum or the lower Riemann sum of f with respect to the partition inducer P. So ganun pa rin, dalawa yung input ng operator L, L for lower, okay? Lower sum of little f, yung function ng little f, at saka yung partitioning P, right? Ito naman ay sum ng mga areas ng mga rectangles where we still have the width of each of the subintervals, okay? Times the infimum of the function values over the ith subinterval. So instead of picking the biggest rectangle or the tallest rectangle that we can form on each of the subintervals, what we are choosing are the shortest rectangles on each of the subintervals because of the choice of the heights m sub I to be the infima of function values over the subintervals. Okay? Kaya siya lower sum yung tinatawag. All right? And I hope you can imagine where I am going here. Gusto kong magtagpo yung upper sum at saka yung lower sum. Kasi kahit same function, pero nagkaiba na yung partitioning na ginamit mo, maiiba na yung upper sum at saka yung lower sum. So kaya nga importante na dalawa yung inputs niya. Nakadepende siya dun sa function at saka dun sa partition inducer na ginagamit niya. Alright? Now, before we proceed to a tangible example, let me just make this quick remark. So the lower Riemann sum is always greater than or equal to, is always less than or equal to the upper Riemann sum. And graphically, it makes sense kasi yung lower Riemann sum, mind you, parehas yung arguments. So parehas yung function, parehas yung partitioning. So ibig sabihin, sa same subintervals, yung upper Riemann sum, ang kinukuha niya ay yung mas matatangkad na rectangles. Kinukuha niya yung sum ng mga pinakamatatangkad na rectangles sa bawat subintervals. Pero sa lower Riemann sum, ang kinukuha natin ay yung pinakamaliliit na rectangles sa bawat subintervals. When I say subintervals, that's the same subintervals we use in the upper Riemann sum. So ibig sabihin, obviously, yung sum ng areas ng mga mas maliliit na rectangles ay mas maliit dun sa sum nung mga areas ng mga mas matatangkad or pinakamatatangkad na rectangles. So I hope you see the triviality of this statement, all right? And then moreover, if f is a continuous function on I sub I, remember I sub I are closed intervals, right? So dahil closed intervals yung mga I sub i's, they are compact sets because they are closed and bounded. If f is continuous, then by Weierstrass's theorem or the extreme value theorem, f will attain its maximum and minimum at that subintervals. All right? So ibig sabihin, yung supremum at infimum sa bawat subinterval actually ay naa-attain sa isa sa mga function values. So instead of saying supremum and infimum, pwede na lang natin sabing si capital M na ginagamit natin sa pag-compute ng upper Riemann sum ay yung mga maximum o yung mga maxima. Tapos, yung mga little m sub i's, kasi sila yung heights ng pinakamaliliit na rectangles, hindi ko na sila tatawaging infima, pwede ko silang tawaging mga minima. Kasi nga, si inassume ko na si f ay continuous dun sa compact set I sub I. Alright? So some tangible examples. Let's consider the quadratic function x squared on the interval 0, 1. And let's consider the partition inducer 0, 1 half, 1, and 2. So, nawala yung inducer. Last minute ko lang kasi din nagdag yung term na inducer. Hindi ako comfortable na tawaging CPI partition kasi sa Math 101, ang definition natin ng partition is a collection of sets. So SCP naman, ang laman niya ay mga boundary points lamang. So I want to call it the partition inducer instead of calling it a partition. Okay? So the partition inducer P given here will partition the closed interval 0 to 2 into 3 subintervals, namely I1, I2, and I3. Okay? So that will give us the lengths of each of the subintervals. Delta 1 is 1/2, delta 2 is 1/2, delta 3 is 1. And then let's take the minima over these three subintervals. Ano yung masasabi natin about x squared from 0 to 2? Its graph is a parabola, all right, or half of the parabola. Actually, hindi pala yung buong parabola. Dapat bounded siya. Ito yung 0 halimbawa. So, ibig sabihin, increasing yung f of x over the interval 0 to 2. So, yung minima ay sa bawat subinterval ay nag-occur dun sa left endpoint. Right? So function value ng left endpoint dito is will surely give me the shortest rectangle over I sub 1. So ang height ng pinakamaliit na rectangle sa I sub 1 ay 0 squared. So little m1 is 0. Sa I2, ang pinakamaliit na function value ni x squared will occur at 1/2. And that will give us 1/4, which will serve as m sub 2. The same thing goes for I3. 1 naman yung makukuha kong function value. On the flip side, to get the capital M sub i's, we need to observe what are the highest function values of f over the subintervals. And again, we have noted that x squared is increasing. So ibig sabihin sa I1, highest function value ay yung function value ni 1/2, which is 1/4. So siya yung value ni capital M1. Sa interval 1/2, ang pinakamalaking function value ni x squared ay magaganap dun sa kanang endpoint. So that means our m sub 2 or big M sub 2 would be 1 squared equal to 1. And similarly, m sub 3 is equal to 4. So that means the lower Riemann sum of f relative to this partition inducer will be the summation of the infima times the length of each of the subintervals. So if you carefully expand this, you'll get this guy and conclude that the lower Riemann sum relative to f with respect to the partition P would be equal to 9/8. Okay. Similar calculations will yield that the upper Riemann sum is 37/8. Okay. And you see here that indeed the upper Riemann sum is greater than the lower Riemann sum as we remarked earlier. Okay? So, yun yung konsepto ng upper at saka lower Riemann sum. Do you guys have any questions? Nakita nyo na rin to sa lower calculus, no? Tinuturo na rin yung upper Riemann sum saka lower Riemann sum. Or ano lang ba? Left midpoint, right midpoint, saka midpoint yung ginagamit. All right, you're too shy to answer. But I guess in one way or the other, you encounter this. Or if not, at least na-imagine nyo kung ano yung scenario. Kasi crucial yung upper Riemann sum at saka yung lower Riemann sum sa pag-construct ng lower at saka upper Riemann integral. Okay? Now, sa Math 36, dinidefine yung upper Riemann sum to be the limit of the summation of the rectangle, summation of the areas of the rectangles using the highest possible heights on each of the subintervals. Yun yung tinatawag natin na upper Riemann sum, upper Riemann integral. Yung lower Riemann integral, siya naman yung limit ng summation ng mga rectangles formed by choosing the heights to be the smallest possible over each of the subintervals. Okay? Tapos sabi natin noon, kung integrable yung function, dapat yung upper Riemann integral ay equal dun sa lower Riemann integral. Pero dito, ayoko rin gumamit ng konsepto ng limits, alright? Limits at infinity kasi hindi natin formally dinefine sa klase yung limits at infinity. So we need to go around this and think of an alternative way to construct these integrals. And it turns out that this would be equivalent to what we would have gotten kung sinunod natin yung Math 36 definition. Okay? Now, without using limits, how do we define the lower and the upper Riemann integral? So first, we will assume f to be a bounded function from the set from the closed interval AB up to the set of the real numbers. Okay, the upper integral or the upper Riemann integral of capital F on the closed interval AB, denoted by this guy. All right. So, medyo level up ang notations natin ngayon. Wala na tayong dx na nilalagay sa integral, just to emphasize the point that this derivation or this development is independent of the concept of derivatives and consequently independent of the concept of differentials. Wala tayong konsepto ng differentials dito, walang mga derivatives dito. Yeah, tinitingnan lang natin ay sum ng mga rectangles. So there's no point in putting a differential in there. Okay? So and then usual usual integral symbol. Ganyan yung some say na ganyan yung notation ng integral kasi it stands for a long letter S, and the long letter S will is the first letter of the word sum. Kaya daw ganyan yung notation para sa integral, because it is just an infinite summation, right? Or this is the limit of a summation of areas of rectangles. So might as call it by an extended summation symbol. So kaya ito yung naisip nila, yung parang uod na nakaganyan, pero yeah, letter S daw yan na elongated. Okay? And to differentiate it from the lower Riemann integral, we will put a bar on top of the integral symbol. So nasa taas yung bar, ibig sabihin siya yung upper Riemann integral. And how do we compute the upper Riemann integral? It is the infimum of all possible upper Riemann sums. Okay? Oh, may typo dito. Ito dapat ay P. Okay? Kukunin natin lahat ng posibleng upper Riemann sum, right? Because here we will take or we will collect into a set yung lahat ng posibleng upper Riemann sum. So ibig sabihin kailangan nating i-consider lahat ng partition inducers ni closed interval AB. Okay? So kaya ganoon yung nangyari dito. So si curly P, siya yung collection ng lahat ng posibleng partition inducers. So pag na-collect ko na lahat ng posibleng partition inducers nung closed interval AB, kukomputin ko ngayon ano yung upper Riemann sum relative to all of these partition inducers. Kukolektahin ko sila sa isang set, tapos kukunin ko ngayon yung infimum nung upper Riemann sums. Okay? So, ibig sabihin, okay, halimbawa, ito yung unang Riemann sum, upper Riemann sum, ito yung pangalawang upper Riemann sum, ito yung pangatlo, ito yung pang-apat. Titingnan ko kasi siya sa lahat ng possible inducers, right? I will define the Riemann integral to be the infimum ng mga u sub i's o infimum ng mga upper Riemann sums. So, ibig sabihin, ginamit ko yung mga pinakamalalaking rectangles, pero yun pala, kukunin ko yung greatest lower bound nung summation ng mga areas ng mga pinakamatatangkad na rectangles. So essentially, I am driving down the value of the upper Riemann sums. Kinukuha ko yung greatest lower bound ng upper Riemann sums to drive it somewhere to the left, kasi nga ang goal ko mapagtagpo yung upper at saka lower Riemann sum. Sabi natin, yung mga lower Riemann sum, lahat sila ay mas maliit sa mga upper Riemann sums. Tapos yung konsepto ko ng integral, dapat medyo somewhere in between siya nung upper Riemann sum at saka lower Riemann sum. So what I want to do is to make the value of the upper Riemann sum smaller and smaller. So that's why I am taking the infimum para pumunta siya ng konti sa gitna. Alright, kukunin ko yung pinakamaliit na lower bound o pinakamalaking lower bound ng mga upper Riemann sums. So simula, napakalaki ng mga upper Riemann sums. Pag kinuha ko yung infimum, makukuha ko yung pinakamalaking lower bound. Alright, kaya ganun siya din-define. Now, similarly, the lower Riemann integral of the function f on the closed interval AB is given by the supremum of all lower Riemann sums. So, dapat ito uli ay P. So kukunin ko ulit lahat ng posibleng partition inducers, kukomputin ko yung lower Riemann sum gamit lahat ng mga partition inducers. So that means meron ako ditong L1, meron ako ditong L2, L3, L4, L5, pero wala ako dapat ditong makukuhang lower Riemann, wala ako ditong makukuhang L. Kasi laging mas maliliit yung mga lower Riemann sums kaysa sa mga upper Riemann sums. Alright? So maliliit yung mga lower Riemann sums. Alright? So pag kinuha ko yung supremum niya, alright? Supremum ng mga L's, kinukuha ko yung ano nga ba ang supremum? LUB, least upper bound. Kinukuha ko yung pinakamaliit na upper bound. Pero upper bound yon in the first place. So ibig sabihin, I am driving the lower Riemann sums higher and higher, pakanan ng pakanan, hanggang mag-meet sa gitna yung upper at saka yung lower Riemann sums. So yun yung konsepto. Bakit baligtad pala? Yung U, kinocompute mo siya as supremum times width of the rectangle, pero in the end, kinukuha mo yung infimum niya. The reason, malalaki na masyado yung mga upper Riemann sums, gusto ko siyang higitin pabalik sa gitna, kukunin ko yung infimum. Ganun din yung sa lower sum or sa lower integral. Yung mga nandito sa loob, mga lower sum sila, so maliliit sila in the beginning. But I want to drive it near the middle to meet the Riemann, the upper Riemann integral. So kailangan kong kunin yung least upper bound ng mga supremum, least upper bound ng mga lower Riemann sum. And essentially, when they meet at the middle, we say that f is Riemann integrable. Riemann integrable siya kapag yung upper Riemann integral ay equals sa lower Riemann integral. And whatever their common value is, yun yung tatawagin nating integral or the Riemann integral of f on the interval AB. Okay? So maraming laman pala yung definition 5.3. We define the upper Riemann integral, the lower Riemann integral, the Riemann integral, and what it takes for f to be Riemann integrable. Okay? Pero sa preamble ng definition 5.3, restricted na tayo sa pag-work sa mga functions na bounded. So yung function dapat ay bounded sa isang closed interval AB. Alright? So any questions? I hope this derivation makes sense. Talagang ang tagal kong dinidiscuss to usually. Just to give you an idea how this is done without limits, how this is done without derivatives. Kaya nga dito, hindi na necessary na may dx pa. Okay? That's why it's not difficult to believe na yung calculus was invented independently by two persons, by Sir Isaac Newton and by Leibniz. All right? Kaya madaling makumbinsi yung mga tao na hindi sila nagkopyahan sa pag-discover ng calculus. Mas sikat nga lang si Newton, and Newton developed it via derivatives kasi yung theory niya of fluxions. So mas derivatives yung focus niya. And I believe si Leibniz mas integrals yung pinagsimulan niya. All right, so, and then they met somewhere in the middle and they proved the equivalence of their two theories. And that's what we know now as elementary calculus. All right? Now let's look at some examples. So let's consider the constant function c. Okay, the constant function c obviously is bounded on any closed interval, say closed interval AB. All right? Tapos, pag nag-consider ako ng kahit anong partition P or kahit anong partition inducer ng closed interval AB, lagi kong makikita ito. Yung lower Riemann sum, kahit ano pa yung partition inducer, alright? Kasi sum lang siya ng little m times delta I, okay? Tapos, si little m, lagi naman siyang equal kay c. Kasi constant nga yung function, so ang minimum function value ay equal lamang kay c. So this guy will be replaced by c. Now it is constant with respect to the summation index I. So it can come out of the summation. So meron tayong c sa labas. And this will just be the summation of the lengths of the subinterval or the widths of the subintervals. Pag inad ko lahat ng mga widths ng mga subintervals, all right, remembering that P is a partition inducer of AB, this will just be the actual length of the original interval. And the original interval is A, B, and it has a length B minus A. Okay, So ang lower Riemann sum, kahit ano pa yung partition ay equal kay C times B minus A. So if I get the infimum ng set ng mga lahat ng set ng lahat ng mga lower Riemann sums, alright, where P is an element of curly P, I will get C times B minus A. Kasi ang laman ng set na to ay laging C times B minus A. So I can say that the lower Riemann sum, so I'll get the supremum of this guy, di pala to infimum, kasi lower Riemann integral yung kinocompute ko. So pag lower, kukunin ko yung supremum, okay? Ang supremum niya ay C times B minus A. But the same analysis holds true for upper Riemann sums, all right? So upper Riemann sums, yung capital M mo pa rin ay constant, siya pa rin si C. You'll get C times B minus A as well. If you take the infimum of constant values, siya pa rin yung constant value. So we can say that the upper and the lower Riemann integral of a constant function is equal to value times B minus A. And since the lower and the upper Riemann sums agree with each other, so we say that the function f, or any constant function, is Riemann integrable on any closed interval AB, because and the value of the Riemann integral is C times B minus A, the common value between the lower and the upper Riemann integral. Okay? So medyo, well, with a little bit more work, you can do prove that any constant, any linear function is also integrable on any interval. So siguro what? Sige, yun na yung gawin nating isang problem sa problem set. Provided na hindi ko siya ipoprove sa klase. Alright. So sa PS4, number 1, prove that any linear function is Riemann integrable. Madali ba to? Actually, baka mahirap pala to. Matrabaho ba to? Madaling computein yung lower at saka upper Riemann sums. Sa mga partitionings, baka mahirap pala yung pagkuha ng infimum ng mga upper Riemann sums saka mga lower Riemann sums. Let me think about this kung itutuloy ko to. Alright? Pero let me know kung madali lang siya. Pag may nakagawa na sa inyo, sabihan nyo kagad ako. Tapos gagawin ko na siyang problem set 4.1. Okay? But I'll also think about it if we'll retain it. I'll let you know next meeting, Thursday next week, if we will retain this problem. Okay? Now, an example of a non-Riemann integrable function. This is the...
Didn't get that. The internet isn't reachable.
Nakikigulo si Alexa. Pero ito ay isang counterexample ng isang hindi Riemann integrable na function. Okay? So ito yung Dirichlet function. At makikita nyo, napakasimple ng Dirichlet function. Yung Dirichlet function, consider natin sa isang closed interval 0,1. Okay? O sa closed interval 0,1. Ang value ng Dirichlet function at any rational number on the closed interval 0,1 ay equal kay 1. So, for example, f of 0 is equal to 1, f of 1 is equal to 1, f of 1/2 is equal to 1, right? But for any irrational number, on the closed interval 0, 1, ang value ni f ay 0. So, f of pi over 4 is 0. F of e over 5 is equal to 0. So, as long as irrational, yung input kay f, ang value niya ay 0. So it looks like this function is very simple. Actually, it is bounded. Kasi ang maximum value niya ay 1, ang minimum value niya ay 0. Pero we will see that this very simple function, this is bounded, ay hindi Riemann integrable. Okay, paano? So, mag-consider tayo ng kahit anong partition ng 0, 1. Okay? So, kahit anong pang partition yan, alright? So, consider tayo ng partition, say x sub I minus 1 hanggang x sub I. Ito halimbawa si 0, ito si 1. Right? Pag kumuha tayo dito ng itong interval na to, by the density property of the set of rationals in R and the density property of the set of irrationals on R, sa pagitan ng real numbers x sabay minus 1 at saka x sabay, lagi tayong may makikitang isang rational number. At sa rational number na yon, ang function value ng Dirichlet function ay equal kay 1. So ibig sabihin sa bawat subinterval, ang maximum value ng Dirichlet function ay equal kay 1. So that means capital M sabay is equal to 1 sa lahat ng possible partition cells ni capital P o sa lahat ng subintervals ng interval 0, 1. So that's why capital M sabay is always equal to 1 for all I. So this would be 1, lalabas siya, summation lang ng x sabay, length of the interval. So that means the all possible upper Riemann sums is equal to 1. Pag kinuha ko yung infimum ng lahat ng mga upper Riemann sums, alright, ito ay magiging infimum lang ng set containing 1. Alright? Kasi pare-parehas 1 yung mga upper limits, yung mga upper Riemann sums, kahit ano pa yung partitioning. O kahit ano pa yung partition inducer P. Infimum ng constant ay yung constant. So ang infimum niya ay 1, so ibig sabihin yung upper Riemann sum ay equal kay 1. Okay? On the other hand, as I've mentioned, there is an irrational number between x sub 1 and x sub 0. So meron siyang irrational number. At sa irrational number na yon, makukuha ng Dirichlet function yung minimum value. Yung minimum value na 0. So ibig sabihin, laging may number sa kahit anong subinterval na ang function value ay 0. And that's the minimum possible value for the Dirichlet function. That means the infimum of all function values on any subinterval of the closed interval 0, 1 will be equal to 0. Okay? So ibig sabihin, lahat ng lower Riemann sum would be summation of 0 times the width of the subintervals. But when we multiply this guys, so we will just get summation of 0, which is equal to 0. And then kukunin ko yung supremum ng lahat ng mga lower sums. Pero lahat nga ng lower sums ay equal lang kay 0. Supremum ng set containing 0 ay equal kay 0. Therefore, ang lower Riemann integral ay equal kay 0. Now, the upper Riemann sum is different. The upper Riemann integral is different from the lower Riemann integral. So we say that the Dirichlet function is not Riemann integrable. Okay? And this is one such function na napakasimple pero hindi siya integrable. Okay? So sa graduate studies nyo, pag punta kayo sa Math 230, measure theory, or real analysis or functions of real variables, however it is called, usually madidiscuss nyo yung konsepto ng generalization ng Riemann integral we call the Lebesgue integral. Okay? Kung saan yung mga function as simple of the Dirichlet function will be integrable. So medyo babaguhin nyo yung definition ng pagiging nung integral. The nice thing about the Lebesgue integral is that it is an extension of the Riemann integral. Lahat ng Riemann integrable ay Lebesgue integrable. Kung ano yung Riemann integral, yun din yung value ng Lebesgue integral kung Riemann integrable yung function. But there's an additional nice property that some nice functions that are not Riemann integrable will be Lebesgue integrable. But that would be for your graduate studies. Pero yun yung idea. Okay, now we will look at several lemmas before we come up with a nice result here. Pero i-note muna natin ito. Itong series of inequalities na to. And I think some of these would be obvious. All right. Okay. Itong part na to ay obvious kasi ang idea nito ay yung lower sum ay laging less than or equal sa lower Riemann integral. And this is true kasi yung lower Riemann integral ay supremum ng mga L's. So ito ay supremum, siya ay least upper bound. So upper bound siya in the beginning. That's why this is less than or equal to. And if we go to the other side, doon naman sa kanan, all right, ito naman yon. Okay? And this is also trivial kasi nga ang upper Riemann sum ay infimum ng mga u. So dahil infimum siya ng mga u, siya ay greatest lower bound. So lower bound siya in the first place. Kaya siya ay mas maliit sa mga upper Riemann sums. Okay? Now, we haven't proven yet yung nasa gitna, na yung lower Riemann sum ay less than or equal to sa upper Riemann sum. Actually, I think you can imagine what's happening there or kung bakit totoo yung inequality na yon. Pero this is proven in lemma 5.1. Okay? Tingnan natin how this was done. Okay? So since little m, okay, si f ay bounded by assumption. Okay, here we are assuming that f is bounded, all right, on the closed interval AB. So there exists a little m and a capital M na true yung inequality na yan. Okay. Then we want to show this is true. All right. Ano yung sinasabi niya? Lahat ng lower sum, actually hindi pala itong gaano ka-related dun sa gitna. Ito yung gusto nating i-prove eventually. Pero para pala ma-prove ito, kailangan ko yung series ng mga lemmas. Okay? So dadaan ako sa iba't ibang mga results bago natin ma-conclude na totoo yung inequality na yan. Even though mukhang obvious siya, pero let's try to prove it rigorously. Okay? Now, 5.1. So suppose f is bounded, so there is a little m and a capital M, so that this is true for all x in the closed interval AB. And let's suppose P is a partition inducer of the closed interval AB. Then we want to show that this is true. Where little m is the infimum, actually sinabi na siya dito, at si m ay yung infimum, supremum. Okay. We want to show this inequality, but actually it's pretty straightforward. Okay. So kung kumuha tayo ng isang partition inducer na si capital P, tapos kukunin ko yung maximum at saka minimum sa bawat subinterval. All right? Little m being the infimum all throughout being the infimum of function values all throughout the interval AB, siya yung infimum ng buong interval AB. So ibig sabihin dapat mas maliit siya sa mga infima sa bawat subintervals. Kasi sa subinterval x sub I minus x sub I minus 1 to x sub I, pinipili mo lang yung pinakamaliit. Pero sigurado tayo na yung infimum na yon ay mas malaki kesa dun sa pinakamaliit doon sa buong interval AB. Alright? So what I'm saying is, halimbawa, ito yung m. Okay, ito na yung pinakamaliit sa lahat ng function values sa closed interval AB. Pag kumuha ko ng m sub I, sige, ganito na lang. A, B, alright? Tapos ito yung interval x sub I minus 1, x sub I. So si m, siya yung infimum sa buong interval. So, teka, drawing ko siya ng mas... okay. Halimbawa, ito yung function natin. So si m, siya yung infimum sa buong interval. So ito si little m. Yung m sub I, siya yung infimum sa interval x sub I minus 1 until x sub I. So siya yung pinakamaliit dito sa interval na to. So ibig sabihin, ito lang siya. Or kung nandito man. Pero siya yung pinakamaliit sa x sub I minus 1 hanggang x sub I. Siya si little m sub I. So sure tayo, si little m sub I ay mas malaki kesa dun sa little m. Kasi si little m, siya na yung pinakamaliit sa buong interval AB. Si m sub I, siya lang yung pinakamaliit sa ith subinterval. Alright? So I hope that is clear. Tapos yung kabaligtaran naman, yung mangyayari dun sa supremum. Si m yung supremum sa buong interval AB. So siya na yung pinakamalaki sa buong interval AB. Si capital M sub I, siya yung pinakamalaki sa ith subinterval. So definitely little m would be less than capital M. Right? Kaya madaling i-observe yung inequality na yan. Tapos na rin tayo dito. Pero yung nasa gitna, actually obvious din itong nasa gitna. Si M sub I, siya yung pinakamaliit sa ith subinterval. Si capital M sub I, siya yung siya yung pinakamalaki sa ith subinterval. So definitely, this inequality is true. All right? So I hope justified. Eto, naniniwala na kayo sa inequality na yan. Tapos, ang gagawin ko, i-multiply ko both sides i-multiply ko all sides by delta x sub i's. All right? Multiply all side by delta x sub i's. All are positive, so it's fine. The inequalities won't change. And then I'll take the summation over i's. So, pag nag-take ako ng summation, hindi pa rin mababago yung inequality. So that's how this guy follows. Okay? But remember that delta x sub I is equal to b minus a. All right? So si M, lalabas yan nung summation kasi wala siyang I na kasama. So this guy will be M times b minus a. Kasi lalabas nga yan. The summation ng x sub i's, ng delta x sub i's ay equal lang kay b minus a. Tapos ito, si capital M, lalabas din yan. Capital M times b minus a. All right? And then, etong nasa gitna, eto lamang ay lower Riemann sum of F relative to a partition P. Tapos, eto naman, by definition, siya yung upper Riemann sum of F relative to P. And essentially, we get the required inequality. All right? So, yeah, that ends the proof of lemma 5.1. I think tatlo yung lemma na kailangan natin para ma-prove ito. So let me borrow some few minutes. Sorry kasi naputol yung internet ko kanina, so I need to compensate. Hopefully, prove natin itong isa pang lemma, yung lemma 5.2. So, but lemma 5.2 talks about a refinement of capital P, or a refinement of a partition inducer, or a partition. Now, we consider two sets, capital P and P star, and let's assume that they are both partition inducers of the closed interval AB. Then we say P star is a refinement of P if P is a subset of P star. Okay? Tinawag siyang refinement, so ibig sabihin parang mas pino yung partitioning na makukuha natin mula kay P star kaysa kay P. And that will happen if P is a subset of P star. Okay? So tingnan natin kung bakit ganun yung definition. Tingnan natin yung example 5.5. So si P, na-consider tayo ng partition inducers of the closed interval 0 to 2. Okay? Si P natin ay ito. 0, 1, and 2. So 0, 1, and 2. So ibig sabihin, ito yung partition. So meron tayo ditong, meron ako ditong I1. Tapos ito naman yung I2. Bakit naging 2 yan? 1 yan. So ito yung I1, ito yung I2. Yan yung partitioning induced by capital P. Now let's consider P star. Si P star ay ito. Alright? And clearly, P is a subset of P star. Kasi si 0, 1, 2, 0, 1, and 2, nandun sila kay P star. But how does the partitioning induced by P star look like relative dun sa itsura ng partitioning induced by capital P? Tingnan natin. So 0, tapos 1/2, 0, tapos 1, tapos 3/2, tapos 2. Alright? So ito naman yung partitioning induced by P star. Gamit ako ng blue. Ito yung I1. Ito yung I2. Ito yung I3. Ito yung I4. Okay? So makikita nyo, mas maninipis yung partitioning induced by P star or yung subintervals induced by P star kesa dun sa subintervals induced by capital P. So parang pwede nyo isipin yung mga subintervals kay induced by P ay nahati pa sa mas maliliit na subintervals induced by P star. Kasi kung mapapansin nyo dito, okay, si I1 na nanggaling kay P ay nahati sa dalawa. Kay I1 star at saka kay I2 star. I think I am lost. Okay, hopefully nakabalik na ako. Can you send me a chat kung nakabalik na ako? Sorry guys. Ang gulo ng internet connection ko ngayon. Pero yun yung idea. Bakit siya refinement? Si I1 na isa sa mga subintervals kay capital induced by capital P ay nahati sa dalawang subintervals. Nahati siya into I1 star at saka kay I2 star. Right? Yung I2 induced by P ay nahati sa dalawa. Nahati siya kay I3 star at saka kay I4 star. Alright? So kaya ang tawag natin sa kanya ay refinement. Yeah, ayaw makisama ng internet connection ko today. Let me see. I don't know if you are. So I hope. Hello. Yeah. Yeah. I think I'm back now. So yun yung konsepto ng refinement. So pwede niyong isipin na yung subintervals induced by one partition ay nahati pa into two or more subpartitions or subintervals within the partitioning. Okay? All right. So I think pinapatigil na ako. Ayaw nang makisama ng internet ko. So let's call it a day. Let's call it a day there. So we finished definition 5.4 and example 5.5. So on Thursday next week, I'll start talking about lemma 5.2 and hopefully some part of section 5.2. Pero pag hindi ko siya talaga, or bibilahin ko yung araw, pag hindi ko siya kayang tapusin, I might record different I will record a different lecture para mag-compensate para dun sa wala nating pasok sa Tuesday, okay? So again, I apologize. It's quite embarrassing about my internet connection, but I hope the message still got across. So on Thursday, we'll start at lemma 5.2. Let me know kung medyo magulo yung discussion ko ng refinement because we will be using the concept of refinement for lemma 5.2. And then kung kukulangin tayo uli ng oras, magre-record ako ng isa pang lecture para matapos natin ito. So pero Tuesday will be a free day for you next week. I'll just give a quick homework for derivatives, okay? And don't forget guys, right before midnight tonight, submission ng problem set number 3, okay? So that's it for today. So thank you guys for being patient with me today. Let's see each other again on Thursday next week. Bye, everyone.
Sir,